19th century. If you have a hot black object, it radiates light of all frequencies. And if you run it through a prism or a diffraction grating, you can split it across into the colors of the spectrum. And these represent the different wavelengths of light. And this is what we would call a continuous spectrum. Well, if you put a gas in between the white light and the prism, what you end up with is certain bands that are absorbed by the gas. And we call these the absorption spectrum. And the wavelengths of these bands represent photons of specific energies that are absorbed by the atoms in the gas. And each type of gas has a unique band structure, and this could be like its fingerprint for identifying what the gas is. Now, if you heat a gas, it will emit light, and the hot gas has excited electrons that when they relax fall down to lower energy states, and these can give off a photon. And this is what we call an emission spectrum. So in an emission spectrum, the gas is giving off light of color or frequencies or wavelengths equivalent to those that the gas would absorb if it was a white light was passed through it. Okay? So now we want to look at how do we account for these. And some of the earlier people like Andres Angstrom made lots of data collecting line spectra from many elements. And Balmer, who was a mathematician, came up with an equation for calculating the visible emission spectrum of hydrogen. And this is the equation here. And what we're looking at here is an emission where an electron goes from a higher state to a lower state. But in this equation, we're not recognizing energy states. And what we're going to say is that these quantized numbers, n is an integer, must be greater than 2. So it could be 3, 4, 5, or 6. Now, Rydberg came up with a more general equation. And in the Rydberg equation, we have transitions to multiple lower energy states. So ultraviolet radiation, which is of highest energy, goes from outer orbitals down to the n equals 1 state. The balmer, which is the visible, goes to the n equals 2 state. The Passion, which is in the infrared, goes to the n equals 3 state. And there are other ones. Only the balmer's lines are visible to the human eye. Now what we want to do is take a minute and derive the Balmer equation from the Rydberg equation with the condition that the ground state, the n equals 1 state, is going to be equal to 2, and we will derive the Balmer constant for visible radiation. Okay, so here we have the Rydberg equation. The reciprocal wavelength is equal to the Rydberg constants times, this is an inverse square type function, times the reciprocal of the quantum numbers squared. Here we go from the n1 to the n2. And we have the condition that n2 must be greater than n1. Now, for the visible radiation, the value of n1 will equal 2. And we're going to set this n2 just equal to n, so we can derive the Balmer equation, okay? So the first thing we want to do is we need to put these under a, we're going to solve for lambda. We need to put these under a common denominator. So I'm just going to write over here 1 over lambda r, and I'm going to put the r over here for now, we'll bring it back, is equal to, now, I want to put these under a common denominator. So if I multiply the first term by n2 squared over n2 squared, I get an n2 squared on the numerator and an n1 squared, n2 squared on the denominator. Now I subtract, and I'm going to multiply this by n1 squared, n1 squared. And now I have these under a common denominator, okay? Now, if I'm solving for lambda, I need to take the reciprocal of both sides. So I get lambda r is equal to n1 squared, n2 squared over n2 squared minus n1 squared. And we note that n1 is equal to 4. So this is equal to 4 times n2 2 squared over n2 squared minus, now n1 is equal to 2, or 2 squared, which is 4, which would be equal to 2 squared. Okay, and now I can say lambda is equal to 4 over r n2 squared over n2 squared minus 2 squared, which is equal to 4 over the value of r, which is on the slide up there, is 1.1 times 10 to the 7 reciprocal meters, which means meters goes up to the denominator, times n2 squared over n2 squared minus 2 squared. And this is equal to the value of b, which is 3.645 times 10 to the minus 7, which is the same as 364 nanometers, because this is reciprocal meters in the numerator, but that's meters, times n2 squared over n2 squared minus 2 squared. So we can see now that this is the value of b, the Balmer constant, and this is a condition of the Rydberg equation when the lower energy state is equal to 2, and we're describing the equivalence of an emission. If on your assignments, make sure that n2 is always a greater number than n1, and then you can solve this.